Let let me do a short briefing on what are we going to continue studying. We stopped last time at these parts with input-output mode. We've seen the set socket option with reuse, address, and broadcast. And we'll see today some the last part from the input-output mode. And I'm not the input-output mode. Yes, one of it is materialized here, the select, mostly select, not pool. Let me just pick up, I don't have the tools again. So we will see this part. Pool is something similar today. So we will see this part. Pool is a bit similar. We've seen blocking. We haven't seen non-blocking, and I'm not sure if it's appropriate. It is, but I'm not sure if it's useful for you now for us to approach this. If you want, we can take a look at it. It's basically the same thing, the same programming. You just set the socket, as I told you last time, into non-blocking mode, and then you handle all the stuff that comes together. That means whenever your calls will block, in fact, you get an error and you need to do some other stuff before calling the socket or the input-output calls again. And from we had at some point, yeah, here, we saw this approach, and we are going to see this one today. Concurrent multiplex servers. Up until now, we had to create processes or threads in order to be able to serve multiple clients at the same time. And we will see now a different approach where we won't be needed to create those in order to those processes or threads, but we will use a different approach, that of select, in order to be able to handle multiple things at the same time. And last time we stopped kind of here, so I won't be jumping from the presentation through the presentation again, so I'll promise right now we are going steadily through it. I just wanted to remember where we stopped last time. So I have some questions. We stop here. Blocking input-output operations. And I want to show you, we want to discuss over this slide and over these examples, what do you think it will happen, for example, in this case here. Suppose we have a client that has this operation in sequence and the server this operation in a sequence. Then we need to discuss with the sequence what is happening, and then what is happening from the timing point of view. Suppose we have the client starting, and let's say there is one operation interleaved. That means the client does a write, and from the timing point of view, the server, how somehow it executes at the same time a read. And another write, the server another read. The client a read, and then the server a write. What does it happen step by step, and what is the final outcome of this instruction sequence? Anyone?
Well, everything should go on fine, right? Because the client writes and then the server has what to read. Then the client writes again, the server again has what to read. And then when the clients will block and the server will anyways write, so it will unblock eventually.
Yeah, you're right. And what if these are happening, let's say if we have a if we have a time, let's say a time graph here. We go from T2. So they are happening absolutely in time, as you see here, from 0 to T1. The client gets to execute write, write, read, and then the server later on in time does read, read, write.
Again, it should be fine because the two writes will be on the socket and the server will be able to read them, and the client will again wait for a write.
Okay.
Well, what can happen is that if you use a buffer for reading and you write into, like the client writes 2 times and the
Yes.
server is reading into a buffer, it can read everything that was written there and it will wait on the second read because it has nothing to read.
Yeah. Very good remark. This is what I wanted to get to. Think of what is happening if the client manages to write not so much data, let's say 100 bytes here, 4 bytes here. And this one, the first read goes with 200 bytes. What is happening at that point is that if things are happening with T2 larger than T1, the first read here read both 104 bytes. Write 1 plus write 2 of the client. And what is happening in that at that point?
It blocks on the second read.
Yeah, the server will stay blocked on the second read, and the two processes are kind of out of sync. Now, what is happening with the second scenario? In the second scenario, we have the client write, write, read, and the server write, read, write. Suppose again, right, just let's talk generally. In general, we have two writes, one write from the server. Is there a problem with that? If we have
No.
writes somewhere in parallel. I want you to understand with this how you should be writing code. Because I've seen during the lab examples where people is just thinking, okay, I'm writing something, the other part should be, should be reading at the same time or not. And that's the question. And how much should I write? How much should it read? Just go over me with the answers, because if I'm talking too much, and if you just wait for me to finish, then you'll never get a chance to answer. So just go over me, and I will stop at the point when you say something. I will stop.
There's no problem with the write.
Yeah. So basically, what we are saying right now is that if both are writing at the same time, or but if this goes like before 0 T1, and we have on an absolute time T1, T2, and T1, sorry, T1 is smaller than T2. Let's say +1. +1. In this case, do we have something abnormal here? We have two writes, one read. So this read will be what is happening. It will normally, in the general case, block here. And we have write, read, and this read at this point will normally consume the two. I mean, one of the or the two writes, depending on the speed. If just the first write has managed to get at the point where I'm reading here, but let's say we are in this situation. So this one starts, it finishes, and then this one starts and it finishes. So I have 2 writes and 1 read. I have a write, a read. This read will consume in this case, because we are in this scenario, consume both reads, both writes, sorry, W1 plus W2. And then we have another write, which actually in this case, I'll stay not. Go, Andrei. Not consumed, but basically nothing bad happens as we look at it. What is happening in the third case? We have read.
Both client and the server will block because both of them will wait for someone to write, and nobody will.
Yeah, so in this case, we have a typical scenario which is called, how does it call it, this situation when we have these things and this?
Deadlock.
Exactly. If you do something like that, it definitely gets to a deadlock. If you start both with a read, then we get a deadlock because the client starts reading, nobody writes to it. The server starts reading right away, nobody writes to it. So they will be both be locked or blocked reading indefinitely, and no one will be able to advance.
Well, wouldn't it just depend on how much it reads? Because if it writes, I don't know, 5 bytes and the reads are only 2 bytes each, then it won't really block.
Yeah, but they are both starting with a read, while no one has written to the other side.
Yeah, well,
So
it depends on the size that they read and the size that's written.
Yeah, it's not really like in this approach here, particularly here, when both start with reading. Although
yeah, that's what you mean. Yeah, that's right. It will block because they both.
it will block
with...
definitely. Now, are you sure this is the only situation where we might get to a deadlock? If we look again at the 3 examples here. Take a look at second example. Second example, as we looked at it up until now, it should work. We have 2 write, 1 read. We have write, read, write. We assume from what we discussed up until now that what it could happen is that, for example, the first read here will consume only 1 write or 2 writes from the client, and the read here from the client might consume, for example, just the first write, and the second one stay not consumed, generally. What if I'm writing here, let's say, 1 gigabyte of data? And what if I'm writing here 1 gigabyte of data? A lot of data. A lot of data that usually cannot be accommodated in a single step. That's why I put this large amount so that it's clear it's not something we play with. Something that it cannot be accommodated by buffering over TCP because no operating system sanely implemented will allocate that much buffer space into the TCP or whatever UDP, and into the TCP because the UDP we're not even talking. UDP is not allowed to send more than 64 kilobytes at one time. So with TCP, if we send 1 gigabyte of data here, 1 gigabyte of data here, what it will happen in these cases is that the 1 gigabyte writes won't be surely satisfied by neither the client nor the server from the writing point of view, because they won't be able to write that, to send that to the other party and ensure and get the confirmation, okay, that chunk of data was actually successfully received at the operating system level. I'm not talking about the other application yet. So it will write from this buffer as much data as the other party is capable of buffering and storing temporarily. And it will return back, I don't know, a smaller quantity, and which is smaller than 1 GB, that's for sure. And then this one, again, it will return something smaller than 1 GB. We get to the read part, and depending on how much do we read, we will consume one part of that n here, or the entire n bytes. And then we get the second, the second write. But if we do that here, there is another subtle error that can happen if we don't check. If we don't check the return, if we don't check the write returns, there is another subtle error that can happen here. Subtle error is the fact that we sent 1 GB of data. We just physically send, in fact, I don't know, let's say 1 MB of data. The rest of it, write tells us by its return value of n, which is smaller, it's just 1 MB, that the rest of it could not send it. So we proceed with the second write, and what we have just done here, we just lost the remaining to 1 GB from the first send. With TCP explicitly told us, I wasn't able to send that. You need to redo it if you want to get the data sent correctly. So if we ignore the return value from the first write, we get to the second one, and we kind of lose the in between, the remaining data that was handled by the first, that was not handled by the first write. So there is this is another scenario that it could happen. Other things that can happen, this is the second scenario. The first one is deadlock. I'll put it here. The second one is this one. And there is the third one, is that writes are blocking at some point. And we get the same potential deadlock. Okay, so we have three situations. I see three situations here. You either, apart from the one that you progress normally and that everyone expects, you can get some let's say, not as easy to see from the surface situations 2 and 3, because 1, you can see it clearly. If both are reading, they are going to deadlock, that's for sure. But when they seem to be able to progress normally, depending on the timings and on how much data is exchanged, you can get to 2 and 3. 2 yields data loss, or if we get if write returns with lesser data written, and if writes are blocking at some point because the operating system decides to actually do not return to you until the entire chunk of data has been written, and the writings block is blocking there, and because there is just one read here and there is not enough, let's say, buffer space freed on the server side in order for the first write to continue and finish successfully, this write will write another chunk of data and it will block. It will stay blocked. blocked, waiting for the entire 1 GB to be sent. And in that case, you could get to the same deadlock situation. Okay, so pay attention to these things. It seems fairly complicated. And if you think right now, okay, now there is a lot of stuff that I need to watch for when I'm programming TCP/IP, when I'm programming TCP. Yes, that's true. And basically, if you don't write very large quantities of data, or if you don't do very long sequences of writes without any timing checking on each side, I mean, without taking care of what you're doing in the server, in the client, you can get to those situations. But normally, in a normal case where you just write fairly, let's say, fairly normal amounts of data over the sockets, you shouldn't be getting into this into the 2 and 3 situation. That doesn't mean that you need to refrain yourself from writing large amounts of data, but you need to look at the return values of those calls.
Is there a maximum size to send, to write?
No. The ugly thing is that no, there is no hint on how much data you can send.
Okay.
What you can do if you want to be really sure that nothing bad happens, you can put the socket into non-blocking mode, try to write, and if it tells you I would block writing there, then you know that your write will block, and you don't do it with that amount of data. This is just for your information. Normally, you won't get into these situations because you don't, in the labs, for example, the labs that you implement for the class, you don't get that much quantities of data written, and you don't have that many writes and reads operations to actually get yourself into those situations. But pay attention to them because they might arrive, for example, when later on you're working into a company and you develop something. Okay. That was all about input-output mode and the behavior, their behavior. And I would like us to skip to start starting the select call that I was telling you about. This one, it's this different approach of handling concurrency. And this call, it's not doing any reading or writing operations on the socket, but merely it is a call that watches a set of descriptors for conditions. For example, you can watch as if we take as example what we just talked about, deadlocks and data loss. This can be prevented with select. And that doesn't mean that you will, from this point on, you need to implement all your TCP applications using select. No. Select, it's designed for some situations where it's really appropriate. It doesn't mean that right from now on, because you're afraid of getting into a deadlock or having a data loss situation, you implement everything with select. Let's see what select does. What select does, it takes a number of arguments. The first one is a max FIDI plus 1. That's because I told you it watches a set of descriptors. That's the ID of the largest descriptor plus 1. Descriptor plus 1. Descriptors are integers, at least into Unix operating systems, but they are in the Windows operating system and in most operating systems, in fact, they're just integers. And it needs this information, we will see a little bit later on why, to know what is the value of the maximum descriptor it watches. And then it has three sets. It has a set of descriptors that it watches for reading conditions. It has a set of descriptors that it watches for availability for writing, and it has a third set that we won't be using, and I'm going to draw it with a different color. For exceptions. And it has what is, and it also has how a structure that tells it how long should it wait for something to happen. Okay, so it gets a set of reading descriptors. You put here sockets that you want to watch for, hey, when is data available for reading on these descriptors? A write set is something, hey, when can I write on any of these descriptors? They could be sockets or file descriptors for that matter, or pipes, whatever you want. And this one is, hey, tell me when something exceptionally is happening on descriptors into this set. And the last thing is a timeout. And this timeout, it could be a value or null. If it's a value, it will wait that amount of time. If it's null, it waits indefinitely. It's blocking. And indefinitely. Okay, so if it's null, if it nulls, it blocks indefinitely, waiting for something to happen. So we have three sets of descriptors. We have the dimension of the max, the value of the maximum descriptor and the timeout. These sets are implemented over some bit fields. Okay, let's say fd set is equal with a bit field. We should see it from the point of view of an operating system as something like this. Zero, 1, 1,000. Okay, let's go again, 64,000 and so on. And each of these is 1 bit with a value 2 power 0, 2 power, and so on. Now, when you add a descriptor into a set, you do it with fd set operation. You take your file descriptor and you give it your fd set. And what it does, for example, if you add into the set the descriptor with a value of let's say 2, 3, 2, whatever that is, suppose that is a second, it will set a bit into this into this bit field to 1. Okay, so that bit with index 2 will be set to 1. And as many descriptors as each descriptor gets translated into a bit into that bit field. Okay, and we have some operations, and we will see why is doing like that. It's because we are at the operating system level, and the operating system by itself, it doesn't have sets, lists, maps, dictionaries, and things like that implemented at the raw operating system level. So it implements some sample those data types in the case of select with a bit field. And we have a few calls. fd0, for example, and you give it an fd set, it zeroes all the entries into the bit field. fd set, it adds a bit into the bit field, basically adding a descriptor to it, telling that this descriptor is set into the bit field. fd clear, it sets this bit to the bit corresponding to that file descriptor to 0 into the set, so actually removes it from the set. fd set actually checks after you call select if any of those descriptor it's marked as let's say dirty, like actually there is something, it's that descriptor is set as being available for the operation that you checked on it. What or how do we do select? How do we use select? And now, first of all, why do we need the max fd +1? Because we have a kind of infinite bit field here. We need to tell select that it needs to look into that bit field for how long? Well, for how long? For as long as it hasn't reached the maximum file descriptor. For example, if the largest file descriptor is set here at 65,000, it knows that this is the part from the bit field that it should actually do operations on. Okay. And it tells it how large of a data structure it needs to allocate behind the scene, how large that bit field should be in order to be able to accommodate all your file descriptors. And then the operations on the bit field are simple and or operations, and or and not negation. When you have one bit set up and you want to actually inverse its value. Okay, all the operations translate to logical operations, and all these fd0 set clear checking if it's set are translating to logical binary operations. How do we use them? How do we use this call? Well, we can instruct, we can give to select any of those three sets. If you don't give one, you just specify it with null. Okay, if you give null for the exception set, it will consider that you're not looking for any exceptions. There won't be any descriptors for exceptions. If you give null for the write set, the same happens for the writing condition and for the read set as well. We create sets, basically read and write. We are going to create during this class of computer science. We won't be using the except set. We will see what the exceptions are. But basically, we are going to use read and write. We add descriptors to the read set that we want to watch for read availability. I mean, when we can call read on them and be sure we are not blocking. For write availability, we add descriptors that we want to be notified whenever we can write on them, and that's it. And then we call select either with the timeout. We tell it, I want to watch over those descriptors for as long as 3 seconds. If nothing happens, just return back. Okay, return back, and if the timeout is the condition that returns 0. It returns a positive count of ready descriptors, how many descriptors are ready for their operations from both or from all three sets. And it tells you, okay, you have let's say, for example, it returns 5. That means that from read set, write set, and accept set, you have 5 descriptors that you need to check and do those operations on them. And it returns -1 if any error. Basically, here what you have is when you get interrupted by a signal. Okay, so we can call an API, a system call, or you can use the system call to actually wait for conditions or on any descriptors, but we wait it controlled in a controlled amount of over a controlled amount of time, either indefinitely if we definitely want to wait until something happens, or if we think, okay, let's wait for 1 second, and if nothing happens, I need to do some other calculus, and then I will repeat the operation, the select operation again. I'll wait for another, let's say, half a second. If nothing happens, I will do some other computation. So that I won't, in this situation, I don't want to stay blocked, that my application stays blocked there indefinitely. I still be able to have some control over the flow of my code. Now, what are the conditions that are triggered by on those three? What are the conditions that are triggering on any of those 3 sets? In the readable set, data to read. Okay, that's the most obvious one. Whenever there's data to read on any of those sockets, select will return. It will also less intuitively when the read half connection is closed on that socket. It will also return, sorry. And when a new connection is available, if this is a rendezvous socket, basically, you put it as rendezvous socket into a readable set, and whenever there is a new incoming connection on it, select will return telling you that you can do accept now on that socket, and it will return immediately a new connection to you, a new socket that can be used to handle that client. On the other side, the writable set, it returns whenever there is space available for writing. You can write on that socket, and that write call won't block. And when the write half connection is closed. On that socket. If you write, we have seen in the first, I think, classes that there is a call to the socket, I think was called shutdown, which is kind of similar to close, but only does a half of the operation. Direction could be read or write, and that called on a socket will actually close either the read side of the socket or the write side of the socket. It's like you think of it of a collection of 2 pipes, and you are either closing the reading pipe or the writing pipe, and you can do that with shutdown at some point in time when you work with TCP and UDP application, and that in fact instructs the other party that when you close, for example, my read half of my socket, the other side knows that, okay, I'm not going to be able to write anymore to this guy. So if I call my writing side, then the other party knows, okay, there is no point in reading again from the socket because no other data will be coming in. Now, whenever there is an error on a pending error, okay, we did some operation and then there is an error coming out of that operation, the readable and writable sets will be
I think you turned off your mic.
Okay, thank you. So where did it stop? Do you hear me now?
Yes.
Oh yeah.
Where did it stop?
Like 2 or 3 sentences before.
Okay, so that's not so long. I need to put this somewhere. It will push. Okay, like that maybe. Okay, so whenever there is a pending error and TCP out of bound data, there are some operations that we didn't study. That's why I'm telling you that we are not going to cover this part. Okay, it's just for you to know that it exists. Not studying it. There is some sort of operations, I told you, that with which you are able to actually send out of bound data or something that is called urgent data. You are doing a write over TCP, and suddenly you say, this write that I'm doing, the third write, it's something that is very urgent, and you need to send it out of bound. You need to send it as fast as possible. And if the previous writes are still in the buffers somewhere, or of the sender, or still in transit, or still in the buffers of the receivers, but not read by the other application on the other side, the out-of-bound data will kind of overpass the first two writes and get ahead to the other side. Now, where would you use that? It depends. It's not something that it's widely used in practice. It exists as a possibility, and because it's something exceptional, what I'm telling you is that we're not going to cover it. Okay, with this in mind, select call. Let's see where can we use this this thing. Can discard this, I think. Let me hide, because we're not actually taking the break right now. Put it invisible. Oh, cut. Okay, cut. Now, where? Let me ask you: do you see a typical scenario where select scenario where you would use select?
Timing out.
Yeah, but let's take invent some application that you'll need to develop where you'll definitely need to use. I mean, it will scream for using select. I'll give you a hint because this is something new to you. And I'll develop it. Yeah, it's the break. I think I'll develop it after the break. So let's stop here, take the break. I'll be available. Can I paste back that thing? Yeah. Okay, I'll put this out and let's take the break for 10 minutes and I will be here. But I'll cut the camera. If you ask me, I will hear it. As I'll see you guys in 10 minutes. Okay, so I'm back. Are you guys ready? Can we go on? Continue?
Yes.
Yep.
Yes.
Okay. Hmm. Okay, let's continue. So we started talking about a typical application that screams for for select. We need to think that select is done with the idea in mind that where you need to watch over multiple descriptors. So what if we are to implement a chat application? For example, where we have one, let's say a classical chat application, not
We
a
don't see
peer.
this.
Sorry?
We don't see the screen yet.
Don't see the screen yet. Again. It's shared for me. Right
Okay,
now?
that's- Yeah.
Yep.
fine.
It was,
I Okay, you need to remember me at all times when you take the break. I don't know. This for me the break for 10 minutes was on the screen for the entire break. So sometimes when I switch screens, I see that it loses the screen projection. So chat where we have one server and client and all messages client 1 client 3 client n, they all exchange messages server. So that means we have something like this, the server here, and we have client 1, client 2, client 3, client 4, all having a TCP connection. And we want to implement this application in some sort of room-like functionality. Have any one of you been using IRC implemented in this thing? I haven't, but I've seen it a few times. It was a very popular chat application some time ago, where in fact you connected with the user and there were plenty of what is called rooms. A room is a gathering together like we have now. Right now, this Teams session, it would be a room there where everyone in the chat can write, all the others see what everyone is writing, and we are chatting in a room. Exactly what the general channel, like a channel in Teams, for example. We write, all of us are writing, and all the others that are subscribed to that room can see the messages. And so we have a number of clients connected to the server, and whenever a message is sent by one client, it goes to the server, and it gets dispatched to all the other connected clients, and eventually back to the client that wrote the message. Okay, so we have a server that stands as a middle point that gets all of the messages, and it retransmits the messages that everyone is sending to the others are connected. Can somebody tell me here why would we need select?
because the server is waiting on a bunch of clients and it doesn't know which one will write first, and yeah,
Okay,
it just has to wait for them.
Why can't we implement this with a threading approach? Or why it's not natural with a threading approach? Because if I'm using a threading approach, I can have one thread for each client, read for messages from the client and each thread, and then eventually send it to all of the others.
You wouldn't know the order in which the clients will send messages.
Yes, but I have one client. I have the one client in each thread. So let's say I'm divagating, right? I'm doing something like I'm just thinking for you. I am doing a read operation in each thread assigned to each client. So I'm reading. Whenever I get something, I write to all the others. What will be the problem with that?
Because you need as many threads as many clients you have, but with Select you don't have to work with many threads.
Yeah, that is a quantification problem. Yes, there is a quantification problem there that if we have 10,000 clients, then 10,000 threads, maybe it starts to be a little bit too much on a single machine. Well, let's say suppose I have infinite resources, so I don't really care about that. What will be the other things that will bother us into this approach?
You wouldn't know which thread is currently executing.
Yes, and that will be an impediment where?
In ordering the messages. Like you don't know which message you will read first. Maybe client 1 sends the first message, then client 2, but you read them in the opposite order. Client 2 first, and then client 1.
Take a look at the chat where we have here. We are chatting in general. If all of you are writing at the same time, the server doesn't really care which one finished earlier. It will just display the messages in the order they arrive. Okay, so if I'm sending something, why didn't that get sent? We are chatting here. What is happening with this stuff?
When we are sending the messages from the server, the client needs to listen to them.
Yes, and that will be an impediment because
the server doesn't want to wait for an operation to be ready. It just wants to execute it.
Yeah, that's a good. We are approaching, so we're kind of approaching, but we're not there yet. Let's think from a client point of view. What in a typical chat application a client needs to do? Well, first of all, it needs to wait for typing from user. 2, wait for messages from server. So I need to do these 2 things at the same time. Can I do them with threads? Well, processes is fairly clear that not, that won't be the approach. But can I do that with threads? Can I have a thread 1 here and thread 2 here?
Well, the thread might be blocking the socket.
For example, yes, well, it's blocking, but if I wait for typing from the user, so that would be standard input here. So I'm reading from the standard input, and as long as the user doesn't type anything, or I'm not doing anything really particular in that thread. Then in a different thread, T2, I wait for messages from the socket. And then I need to read them from the socket and write them to the standard output. It will be feasible if you ask me to do that. Only that you'll have a threaded thing that that messes up with inputs, outputs, and then do I really need that? What if I take select, add both standard input and the socket into a reading set, and then whatever happens first, I just do that operation, because the operation that I need to do is just reading either the content from the standard input, either the content that just came in from the socket and displayed on the screen. So the actions will be very short afterwards. And I can do that with select. Now let's take and let's look at what is happening on the server side. You have an client equal and sockets. We need to wait on all of those sockets, and whenever something happens on all of those sockets, I need to write on all the other sockets. Okay, so this is again a scenario where I need to look in a shared state. I mean, I need to have all those sockets available and all those messages coming in into a shared state, and I need to be able to dispatch each individual message to all of the other sockets. So I can do that with threads as well, but practically, as one of you just said before, it will be infeasible with a lot of clients. And it's not natural either, because in fact, you will have different threads. And more than that, whenever you have threads, what do we need to ensure? We need to ensure exclusive access to the shared state. And as things might not be very complicated with a shared state, with only 2 threads, you're only blocking either one of those 2 threads. When we have a large number of threads, that problem becomes less tractable, if you want. I would say that whenever you have to choose between doing concurrent programming with threads with a shared state, or an approach where you don't need to use any mutual exclusion primitives, anything like mutexes, semaphores, conditional variables, and things like that. Whenever you have to choose between threads and something that it's capable of doing the same thing without using synchronization, take the thing that doesn't use synchronization. It's not because I'm telling you so, but because implementing synchronization, it's at all times for humans error prone. I mean, you will do a lot of debugging, and not more than that, you will do debugging. It will work at some time, and then you just put it to production, and it will run on different machines with different timings, and you will get to errors that you never figured it out when you develop the application if the design is not 100% correct. You'll definitely meet a case that you haven't thought of, some error that screws up with the timings in your synchronizations, or one of your threads will just stay into the critical section and will never exit, and it will definitely block all the others, and your application will enter into some sort of deadlock because of that. So things are very complicated whenever we use threads and we have shared state with or critical state that needs to be protected. If you have a mechanism that allows you to do that without that thing, go for that. If it's not a major if it doesn't have a major performance impact, or if it's not the real performance that you get. Most of the time, having a thing that it's working correctly with some small performance impact versus a thing where you're not sure if it's going to work in all cases, well, you'll definitely go for that one that it's working correctly. So with this in mind, let's go and see how would I implement such a thing with a server that accepts clients we have a single room, okay, a single room where all the clients are connecting and they start chatting to each other. And in order to do that, I have the code already prepared it, and you have it into the class web page as well. Let me know if the size of the fonts is correct. It's okay for you. Do you want the fonts to get enlarged, or is it okay for as displayed under my screen?
It's okay.
It's all right.
It's all right. Okay. Now, let's go over the typical client. This is not very long. It's a client implemented on Linux, so it doesn't have the Windows socket part, but otherwise it will work just as it is if you add the socket initialization part and the shutdown part for the library. It will work in Windows without too many modifications. So let's see how would we implement this. So my client will take, or let me just show you how it works, and then let's take over the source code because it will be easier. I have here 3 tabs, all into the same folder. Let me launch the server. Okay, it tells me that it needs a port number to listen on, and I have given it. And let's launch 2 clients. Okay, point client, and it tells me it needs a host. I'm running all on the same host, so I'll just put port 5000 and connect it. And what I have here, it tells me I'm connected to 127.0.0.1, and this is the first message. This is the welcome message that the server sends me. Hi, you are client ID 4 connected to the server. There are 1 client connected. Well, basically you. There are some messages that I printing on the server on the output. These are just logging messages. Let's connect another client local host 5000. Okay, it tells me, hi, you are client ID 5 from this IP and port connected to server, and this is the IP of the server. There are 2 clients connected, and now hi, I am client 2. Send some messages. And if we look on the server, nothing happens. But here I've got something that says on the other client 127.0.0.1 ID 5 and the message, hi, I'm client 2. And if I say here, hello, nice to meet you. Well, I have my message and I have my message sent to all of the others. If I would connect another client, client, this can scale up to as many clients as we want. Hi, I am client 3. Did I miss something? I know, you get the figure, something. And if we look at clients 1 and 2, both go to that message, and that continues on and on. We can continue chatting like this for as long as we want. And by the end, if I want to disconnect one of those clients, I have implemented some special types of messages that says quit. If I write quit instead of sending that message, dispatching that message to all the other clients, in fact, the server disconnects the client, and all the others are getting something like take a look, client with ID 4 has disconnected. Okay, and everyone gets that message, but the other ones are still staying in the chat and they continue. Let's continue. Okay, they are discussing with each other like nothing happened until everyone quits. And when everyone quits, well, nothing happened. The server is still there. The room is still open, but there is no one in there to chat. So that's my typical scenario for running this application. Now, let's take a look into the source code. So in the client, I have two arguments, the host name and the port number. You take the port number, do an integer out of the second argument. Then here, what I try to do, and this is something I want to show you, is I try to convert the first argument, which is the host, with INET AD address by assuming that it could be an IP address. If that's not an IP address and it is your host name, the INET ADDR will fail. But I do that in order to check if it's an IP address or a host name. So if the IP address is -1, that call has failed, I know that that's a host name at that point on. So I assume that will be a host name and try to do get host by name from that argument and get the same IP address that I would have gotten if the first argument would have been an IP address. If I get an error from get host by name, well, then it's neither a host name nor an IP address, so I can't really do anything with that, so just exit. Otherwise, copy the IP address that I've just got into a SOC ADDR structure with the port as well. Just copy the IP address here, then create a socket, put the port as well, and connect to that address and port from the client. And then right now, take a look. I have some sets here. I have a FD set or read and the master. Now there is something I haven't told you during the class, but it was written on the slide, is that after each call of select, the sets that you are passing in to the select call are changed, no matter if something happens or not. Because that's the behavior of select. It changes them. So you need to preserve a copy and pass that copy at all calls. So initialized a read set, a master set, that will be my backup copy that I will pass in at each call. I mean, I will copy into the read set and that pass read set to the select call so that I keep into the master set my clean set, and then that will be changed by the select call. And in order to avoid creating it at all times, I just keep a backup copy of it. Add to the master set the standard input here. What's that? Okay. Add standard input to master set. Then add my socket to my master set. That's pretty much obvious there. And then go into an infinite cycle and do copy the master into the read set. I know at this point on that my socket is the maximum descriptor because the standard input is 0. So whatever I have as a socket, that will be the master, the maximum ID of all the descriptors that I'm watching, and call select with just a read set, because in the client, the only thing I need to know is when I need to read either from standard input or from standard output. The other parameters are null, which means wait indefinitely on the select call until something happens. If I've got an error, just display the message and bail out at this point. Probably I should be handling things here in a different way. I mean, there's not necessarily to get out at all times. Maybe select just what got interrupted by a signal. So I don't really need to get out from the application here, but it will get more complex if I do that. And the code is, we will see the server, it's fairly complex already as it is. Let me indent this properly. Okay, so now when I return from the select call, I get a number of arguments, but I only have two. I only have two descriptors here. So what I do, I check if the standard input is actually checked as ready for operations. If yes, then read from standard input into a buffer and send that to a socket and check for errors. If something bad happens, well, just exit the client because I couldn't write that to the server. Check if the socket was checked by the select call, and if yes, does it have this automatically indent, automatic indentation? Edit, toggle indentation. I don't see. I'll look at it. Indent. I don't see any indent. So read from the socket. If I've got an error reading, then I know that the socket, the TCP connection is somehow broken. So I don't have anything. I mean, in a teaching project, I will just exit. Probably in a real normal application, I will just reconnect my socket and retry all the stuff. But right now, I'm not doing that. And write it to the standard output. And this happens indefinitely. Just wait for something to happen from any of the standard input and the socket, and either send the message to the other side or display it on the screen. And that's it. The client, it's quite simple. Now let's look at the server. The server, it's a bit more complex. It has more to it. We have some global state here into the app. And let's take a look at the main. The main, what it does, it takes a port number. Again, it converts it to an integer. I create a master set and the read set. And I initialize them with zeros. Create the rendezvous socket here. Set the thing that I just told you last time. So reuse address. Okay, set socket option on a listener. The socket that I'm trying to bind, if I abruptly stop my application, my server code, and launch it again, normally it will use this option to allow it to rebind it to the socket which is still not made, to the port which is still not made available by the operating system. This will enable me to do that. Then bind afterwards. If I did that set socket option, normally I shouldn't get any bind error here. Set the listening queue to 10 this time because I'm expecting this chat server to have lots of clients. Add the listener to the master set and track the maximum socket descriptor. At this point on, the FDmax will be the listener. And then enter into a main infinite loop as in the client, where the master, I only have the rendezvous socket at this point into my reading set. Do select, again, just with the reading set and with FDmax that got tracked here, +1. And, well, bail out if there is an error. Afterwards, check all the descriptors. For right now, I only have one, but when I would have lots of clients connected, I'll have many descriptors here. So for I equals 0 up to FDmax that is tracked, you'll see how. Check if any of those descriptors is marked as available for operation. If it's the listener, in the particular case, I take it into the current variable here. And if it's the descriptor, if it's the rendezvous socket, I need to do something like accepting a new connection. So call accept on the listener. Display an error if there is an error. And if there is no error, add the new accepted client into the master set. And if the new socket, just keep up with the master descriptor. If it's larger than FDmax, just update FDmax. And print log some message to the console. This is the select server, new connection from, and get the IP address out of that socket. And the ID of each client, as you see, it's descriptor value. Get IP address, we will take a look what it does. It extracts from a socket either the locally connected, either the local IP address or the remote IP address, depending on how is it called, with true or false here. Increment the client count. Prepare a welcome message from the client. Hi, you are client, I don't know, connected to server, whatever, and so on. And I give it the ID, the socket descriptor, the get IP address, get port, and the port get IP address of the server and the client count. So it tells basically to the client that you are client whatever connected to the server, and this is your IP and port. And it sends that message, welcome message, to the new client. And we were in the case that where the descriptor that I checked was the rendezvous socket. Otherwise, if it's not the rendezvous socket, I know it's one of the sockets of the client. So what I do here, it's read from that socket one message. If it reads nothing, it will just print something. It just log something to the console. If it's an error, then decrement the client count, because if I having an error reading from a client, I know the TCP connection is broken. So close that socket, take it out from the master set, and in any other case, well, I haven't had any error, just okay, the message has already been read here. Compare it first with quit. If my client just sent quit, that's not something I want to send to everyone. That's just an indication that he wants to quit. So I'm telling it back a message, a confirmation message to that client, and send it. Okay, request granted, you can quit. And tell all the others that client, whatever, disconnected. And I have a function here, send to all, because I don't want to iterate over all the sockets here into the main loop. I'll just wrote a function for that. Decrement the client count if it requested to disconnect. Close that socket, take it out of the master set. Now, if it wasn't a quit message, what I do is prepare a header for that message and send the message with that header to all the other connected clients. Now let's take a look at what send to all does. It's a short function here. It takes a buffer and a number of bytes, and what it does, it goes from G0 to FD max, which is tracked globally. If FD is set in and if it's different than the listener and different than me, just send over that descriptor the message. Okay, so send to all the others the message. And take a look, I'm using the set. I don't need to track separately all the sockets that I have. I just track if that descriptor is already in my set. If it's already there, I know it's a client. So I don't need an array of sockets that I will need to go over it. I can do that as well, but at that point, if I manage a different array with all the sockets that I have with all the clients, I would need to also manage that as well. Whenever a client disconnects, I need to take it out from that array, and there is no point in doing that when my FD set already has that functionality. Okay, that's what send to all does. And get IP address with a socket and a direction, local or remote, does get socket name. Which get socket name, what it does, it calls, if I want to get local information, local IP and port, it calls get sock name. If it wants the remote IP and port, it calls get peer name. And in both cases, it gets a SOCK-ADDR structure back. And that is used by get IP address, which returns a string inet and to A from that structure. And that's it. The port does exactly the same thing, get sock name, with which calls the exactly same two function, get socket name or get peer name on a socket. Those two functions return get sock name returns information about the local socket, IP and port, get peer name on a socket gets remote information, IP and port. And that's basically what it is for the server. Okay, you have it into the class web page. You can take it, compile it, and run it, and see how that is happening. What I suggest you to do is to actually, try to place breakpoints either into the client and into the server, and watch it step by step how it goes through the flow of operation into both the client and the server. Are there any questions on this for this client and server? Not. I wanted to do this. Sorry. Control Alt Enter. If not, the source code is in the slides as well, but I find it not so easy to follow when looking to the source code like that. And before moving on, if there aren't any, don't save. If there aren't any, yes, go ahead.
Questions. So I tried to put the client on Windows, but it had a problem with select on the standard input. And is there a solution for that?
Yeah, I think there is a different call for select. It's called W. I think there is a different call that takes yeah, you're right. Yeah, on Windows, this Windows select call doesn't know how to by default doesn't know how to handle normal descriptors and file descriptors and standard input-output descriptors all together. It's not for Windows. It's behind the scene. It's not exactly the same thing. I will take a look because those APIs are kind of changing all the time. So I will take a look on what you should be using in order to do that on Windows and come back to you with an answer. Okay.
Okay.
But it's a good observation. Yeah, it's a good observation that if you're looking at the socket descriptors as well on Windows, it's something like this, socket. But if you look behind the scenes, that is just a type def for the same integer that it's used for descriptors on Unix as well. So there it works. For standard input and standard output, they are handled a little bit. It's because of that standard input and output that they are handled a little bit differently. I will take a look on that and come back to you. Any other questions? Okay, if not, I told you in lab, sorry, and I will open the web page to the lab. To the lab, put it here. Lab 3, I think that everyone, I presume that anyone told you that there is a problem in lab 3, that this one, which uses some broadcast mechanism. I will explain you in a moment what that is. So it's a sort of scenario where this problem here implements a single application that is both a server and the client at the same time. So the paradigm it's a little bit different, and in the past years when I gave this to the development students, it kind of puzzled them because they all thought, how can that be possible to be a client and a server? And it's nothing special. It's just that you play both roles at the same time. You're a client for somebody else, but you're the server at the same time for somebody else. And this application, what it does, you can think of it as of a scenario where you have multiple computers in the local area network, and you want to synchronize the dates in time all together by a voting mechanism. So with that in mind, each of those machines sends a broadcast message, something that gets delivered to all other machines into the network, asking, please give me your current dates and times. It takes those current dates and times from all of the machines in the network, and it does some sort of averaging or voting on the date and on the time, and it sets its own local time with that. And at the same time, all of the other machines are doing that. They are asking for date and times for all the other machines, and everyone is kind of converging by using these mechanisms to some sort of very close in time values for the date and time for all of them. Okay, and this is implemented by using broadcast. I mean, a message which gets delivered to all the other apps on the local area network only. And I want to show you these mechanisms today. And what I wanted to tell you is that if you implement this correctly and you launch it and it works, we cannot test it right now as we are. We cannot test it as we are all together in the same local area network. But if it works, for example, with my standard implementation that I know it's correct, you'll laugh at me, but this is how it is now. In a normal situation, I'll put you in the lab and ask, okay, now all of you run your implementation. If they are working together, if we implement this correctly, you get 1 point added to the first test, to the programming part of computer network that you get at the middle of the semester, probably in lab 7. Okay, so if you present this and it's correct, you get 1 point added into the grade for that part. And you have some hints here on how should you implement this, whether you're using Windows or Linux. On Windows, probably it will be useful. You need some timers because those applications send every 3 seconds something, every 10 seconds something, and then they are taking back results and doing something with them. You have hints here on what to use if you implement that on Windows. If you implement that on Linux, it's fairly easy. You can just create 2 threads, sleep in each one of them 3 seconds and the other one 10 seconds, didn't do something. Okay, now it uses broadcast. Broadcast is something that, I have it here. It's something that, I have a broadcast example here. It uses something that, or is a mechanism that works only in a local area network, okay? It doesn't go over any router. But any message that you send as broadcast, it gets delivered to all the machines inside the local area network. And it does something like, let me erase this. No, not that one, this one, okay. Come on, erase it. We have a local area network. We have a number of machines inside. And suppose we have as IP in this network what is typical at your homes, /24 or / this is equivalent to 255, 255, 255 and a 0. That's a network mask. Basically what this IP, we will start studying next lecture, what this tells me is that IPs into this network are going to be of the shape 192.168.0.0, 192.168.0.1, and so on up to 192.168.0.255. So you see that what I have here varying is just the last byte in my IP address, and this is basically what this net mask tells me. as we are going to study next time. It tells me that the first part, 3 bytes here, are all ones, 255, 255, 255. And that means that these 3 things are mapping here. And these 3 bytes means are fixed, are part of the network, are the network identifier. And the last one, which is not part of the mask, is the host part, the one that can vary to obtain individual IP addresses. And now there is a special IP address in each network, special IP, the largest one, always, or the last one. This one is called the broadcast IP of the network. And it's the break already. The broadcast address of the network is the broadcast address that you need to use whenever you send a message to everyone. And I just need 1 minute here. Broadcast listener, it's a UDP application. As you can send broadcasts to everyone, you can send broadcasts to everyone. It's going to be clear that I have a message starting from here, and it gets delivered to all of those machines if there is an application listening on that port. Because this is happening with just 1 copy of each message, that means that won't work over TCP. It works over only UDP. And in order to implement broadcast, things are fairly easy. You just send a message to that special IP inside each network. You create a socket. This is the broadcast listener, the one that receives messages. I bind it to a port and read. In the broadcast receiver, the application that reads broadcast, usually there is nothing special to do. It's the fairly typical UDP application that has a port, a socket, and reads data from a port. And if that port happens to be the destination of some broadcast messages, then you'll get the message. Now, in the sender, there is something that you need to do. This application takes 3 arguments: an IP, the broadcast address, the broadcast port, and that's nothing special, it's just a port, and a message to send over the network. And I will stop there just to have a few lines. You need, in order to be able to send that, to actually send to that special type of address, you need to set this option on the socket. So broadcast, and broadcast permission is an integer with a value of 1. You give it as to set socket option, and whenever you do that, whatever you send, it's sent to all of the machines that are listening into the local area network on that port. And it's as simple as that. Whatever you send after doing set socket option on a port over UDP gets delivered to all of the machines. So it's nothing fancy, nothing complicated. Whenever you have, for example, a video stream to stream in a local area network, you can stream it over UDP using broadcast. Why? Because it's 1 copy of the message traveling through the network. It won't use a lot of network resources, and it gets delivered to everyone. Okay, I will stop here. You have this example in the web page, and if you don't have it, I need to check. I will add it right now after the class. And yes, you have it. UDP broadcast, it's here. I think it's a different one here, but anyway, and you have it one on Windows, both on Windows. I will add the other example as well that I just shown you. It's basically the same thing. It just sends a message over the broadcast. Now, on some operating systems, the receiver should set the so broadcast option as well. What I suggest you is that in order to be sure, just set it on both the sender and the receiver, and you're sure that you'll be able to send and receive broadcast at the same time. And with this, because we're already in the break, I will stop here. I will stop recording. Sorry for keeping you again. Just stop me whenever you want to get out and take a break. Or you, of course, you can independently leave while we're entering the break. Just wanted to make sure that you get this information to be able to implement your lab. And I will stop the recording right now. If you have any questions, then I will be staying here.